Welcome to The Explainer. Today, we're going after a powerful, totally invisible force that shapes pretty much everything in our world, from those little static shocks you get to massive bolts of lightning.
But to really see it in action, we're actually going to start in space. Take a look at this. This is footage from the International Space Station. Now, in zero gravity, these water droplets are spiraling toward a knitting needle. But why? I mean, the needle isn't even touching them. What is going on here? Some invisible force is literally pulling them right through the air.
Okay, so let's really dive into this mystery. Up on the ISS, the pull of gravity is pretty much gone. And that's amazing for us because it lets us see other fundamental forces, like the electric force, do their thing in ways we just can't see down here on Earth.
To solve this whole thing, we first have to talk about a secret property hidden inside all matter. I mean, everything, from a doorknob to your own body to, yep, those water droplets in space. It's something called electric charge. So, what is this stuff? Well, electric charge is a basic, fundamental property of matter itself. It's the reason for every single electrical thing you can think of, from a tiny spark of static electricity to the enormous power grid that keeps our lights on.
Now here's the thing. Charge isn't just one thing. It actually comes in two flavors. You've got positive charge, which we show with a little plus sign, and you've got negative charge, which gets a minus sign.
But you might be thinking, well, if everybody has charge, why don't I feel it all the time? Great question. And the reason is that most objects are what we call neutral. They have a perfectly equal, balanced number of positive and negative charges. It's just like in math class. If you have a +1 and a -1, they cancel each other out, and you get 0. A balanced object has 0 net charge.
Okay, so we've got these charges. What do they actually do? Well, they create a force, the electric force, and this force is all about pushing and pulling, and it all comes down to two really simple, really predictable rules. Let's check them out. The first rule is super straightforward. Like charges repel, so two positive charges will always push each other away, and two negative charges, they'll also push each other away. If they're the same, they want nothing to do with each other.
And rule number 2? Well, it's basically the universe's ultimate love story. Opposites attract. A positive charge and a negative charge will always be drawn toward each other.
You've seen this a million times. If you rub a balloon on your hair, you're physically scraping negative charges from your hair onto the balloon. So the balloon ends up with extra negatives, making it negatively charged. Your hair, which just lost those negatives, is now positively charged. And what happens next? Your positive hair sticks right to that negative balloon.
Okay, so that all makes sense. We know how charged things push and pull on each other. But what about neutral objects? This is where it gets really cool, and it's the key to cracking our space station mystery.
Seriously, think about this for a second. We just charged up our balloon, so we know it has a negative charge. But a wall is neutral. It's balanced. So why on earth would a negatively charged balloon stick to a neutral wall? It shouldn't, right?
Well, here's the secret. It's a fantastic little trick called polarization. When that negatively charged balloon gets close to the neutral wall, its negative field actually pushes the wall's own negative charges just a tiny bit deeper into the wall. The wall is still neutral overall, but right there on the surface, it's left with a temporary positive charge. So now our negative balloon is right next to a positive surface and, boom, they attract.
And now we have all the pieces. Let's go back up to the International Space Station and finally put this zero-gravity puzzle together.
So let's think about those floating water droplets again. Just like the wall in our last example, these little drops of water are electrically neutral. They've got a perfect balance of positive and negative charges inside them.
That knitting needle, though, that's charged up. And as the astronaut brings it near the neutral water, it does the exact same thing the balloon did to the wall. It polarizes the water droplets. It pushes and pulls the charges that are already inside each drop, creating a positive side and a negative side on every single one.
And that's the whole magic trick right there. This polarization creates an attraction. The side of the neutral water droplet that's closer to the needle becomes oppositely charged, and that creates an irresistible pull. That's the invisible force we saw, the electric attraction that yanks those water droplets right out of the air and into that incredible spiral.
And hey, this isn't just some neat trick for astronauts. This exact same physics is happening on a colossal scale all the time. The bottom of a storm cloud builds up a huge negative charge. That, in turn, polarizes the neutral ground below it, creating an attractive positive charge on the surface. And when that electrical tension gets big enough, you get a catastrophic discharge we all know as lightning.
So let's do a super quick recap of the big ideas. Number 1, all matter has positive and negative charge. Number 2, like charges push away from each other while opposites attract. And number 3, a charged object can actually attract a neutral one by polarizing it, by shuffling its charges around. And that is the invisible electric force we saw at the very beginning.
And that leaves us with one final kind of mind-blowing thought to chew on. The very electric force that holds your own atoms together is trillions upon trillions of times stronger than gravity. So, why is it that we feel gravity's gentle pull every single second of our lives, while this unbelievably powerful electric force remains almost completely hidden?